So we are really excited to have Jeff Anderson presenting to us as part of the GeoDAWG seminar series here in the month of April. Spring is flying by. Just some quick announcements that we have Joe Hughes presenting in May, so be on the lookout for those announcements and links to his presentation coming up. If you haven't already, please join our mailing list. We have a lot of things that go out to it. So join if you can. And as always, we are recording this presentation and we'll upload it to our YouTube channel. So if you have to cut out early or if you missed it, please feel free to join there and view it. And we'll make Jeff's name here, you can see on the bottom. This will become a sim link that will directly pull you to that presentation. And if you know someone or would like to present yourself, please reach out to us and we'll make sure you get on the schedule to hear about your work. So I will pass it off to Anthony, who will give a quick intro to our speakers today.
All right, thank you very much. So just a quick reminder to please try and keep yourself muted unless you're asking a question, and then feel free to raise your hand or enter your question in the chat to get your question seen and answered. So today we're welcoming Jeff Anderson. He's a researcher at NCAR with background research interest in improving predictions of Earth atmosphere and doing so in part via ensemble filter data assimilation modeling. So I'll let you go ahead and get started. Thanks very much for joining us today.
Thanks. It's great to be here. Hopefully we will be successful again with the screen sharing. People should feel free to ask questions at any time. And if the moderators see stuff in the chat or whatever, I think I won't actually see that while I'm talking, but you can let me know too. And let's see. Are we in the right mode at this point?
Yep,
yes.
It looks great.
Cool. Okay, but we're not at the start of the talk. Let's get back there.
I'm gonna say that's the heck of a title slide.
Yeah. You see in the title slide, full screen now.
Yes, that's good.
Cool. So as noted in the introduction, my name's Jeff Anderson. I'm at the NSF National Center for Atmospheric Research. And my primary research areas are in ensemble data assimilation methods. And my group produces something called the Data Assimilation Research Testbed, which is a community facility for doing ensemble data assimilation. It has been applied to many, many Earth system and other applications, including a number of them for space weather, upper atmosphere, and other things. Today, I'm going to talk about some new methods, extensions to Ensemble Kalman filters that I hope will be of interest to some folks in GeoDAWG. I've seen some of your other talks. I know your mission. And so these are methods that make it easier to deal with sparsely observed things where you have more uncertainty and hence more nonlinear relationships. It's also useful for bounded quantities, things like tracers in your model. So if you have specific types of species or other things that have a lower bound on them, these methods are helpful for doing stuff like that too. Now, I know this group is filled with experts on data assimilation, and so my base slide's combining observations with the model forecast. And again, the only point from this slide here is I will be exclusively talking about ensemble methods, this tropospheric example of a spaghetti plot of a 500 hectopascal height indicating that. And again, this schematic is also going to be familiar, I think, to just about everyone in the audience, but there's one point I want to get out of it. So again, data assimilation is combining forecasts from a prediction model, observations from observing system of some type. I'm going to use the term analysis at some point to indicate the result of that process, although it also could be a posterior. And the methods we're going to be discussing are cyclic in that analysis is used as initial conditions for subsequent forecasts with the prediction model. And so you might do this every 6 hours. You do data assimilation, you make a 6-hour forecast from your analysis, you gather observations over some window, you do the assimilation, and you repeat. So these are the types of methods we'll be looking at. And again, these methods can do that sort of prediction problem. They can do a lot of other things, and the tools we develop can do some of these other things. Of course, they can identify systematic differences between the analysis and the prediction model, which are really finding differences between the observing system and the prediction model. Can be used to estimate model parameters, and I'll show one example of that towards the end. I have a lot of experience with estimating things like F10.7 and other external forcing parameters in certain types of space weather applications. One can also learn things about the observing system, the impacts of those observing systems, the errors and other things. However, for today, we'll focus just on that analyses and forecasts of the cyclic standard data assimilation and a little bit about external forcing towards the end. And again, everyone's encouraged as we move into deeper content here, interrupt at any time. Everything I'm going to talk about is really pretty trivial. And so if it's not making sense, it just means that I need to explain it better. So definitely jump in. So I don't do a lot of mathematics. I'm not great at it, but I'm going to do just a little bit at the introduction here. So this is a general stochastic description of what I'm going to call the forecast problem. And so equation 1 at the top there is literally just a forecast model. So I have some system and its state is represented by a vector x, and x is a function of time t. I'm interested in computing the evolution in time of that, so dx of t. And I'm going to describe the model as having a deterministic part, f, and a stochastic part, g. And computing those two, which would normally just be done with some computational code, will give you the next time of your model given the current time. The second part of the forecast problem is the existence of observations. I'm going to assume for today that the observations are available at discrete times k, so those are t sub k, and that there is a vector y sub k of observations available at each time t sub k. And we have a function h, which maps from the model state vector x at time t sub k to the expected value of the observations y sub k. And that mapping also includes some noise, nu sub k here. In the short term, equation 3 says we're going to assume that that noise is normal, unbiased with a specified covariance r sub k, but we will relax that as we go on with the talk. But anyway, the assumption is we can predict what would be observed given the model state by applying h to the model state. In equation 4, we're going to define another vector. It's the complete history of observations, capital Y at tau. So capital Y of tau is simply all the observations y sub little y, little l, that have been available at times t sub l up to and including time tau. So it's all the observations that have ever been taken of your system up to and including this morning when we're doing some sort of data assimilation. And the definition then of our prediction problem, analysis and forecast, are in equation 5. At the left, we have the probability of x, the state of the model, at time t, given all the observations up to and including the current time. And that's our analysis. And the forecast is simply the probability of x at some time that's greater than the current time, given all those observations up to the current time. We could also write down some smoothers and other types of things one might want to do, but these are sufficient for today. Again, one of the things we would have to do is advance our state between times at which observations are available, and that's simply done by applying the forecast model. And in what we're going to do, it's going to be done by applying an ensemble sample of forecast vectors x. But equation 7 says what we have to do once we get to a time where we have observations and we're doing the assimilation part of this cyclic procedure. And we're going to define that process with Bayes' rule. A particular form of it is defined here. So in equation 7, the left-hand side is the analysis that we're trying to find, the probability of x at the current time, given all observations up to and including that time. And Bayes tells us we can rewrite that as the two terms in the numerator on the right. The first one is the probability that we would have observed what we did observe at this time, little y sub k, given our estimate of the state at time k, x sub k, and all the previous times observations. That's called a likelihood. The second term in the numerator is our prior. It's the probability of x, our model state, at the current time, given all the observations up to and including those available at the previous assimilation time. So it is our forecast to the current time. And the denominator is just a normalization, which nicely enough is going to disappear from all the problems we're going to do moving forward. Now, we already assumed on the previous slide that at least initially the noise associated with the observations is white, so uncorrelated in time. And that means that the observations at the current time, the distribution of those, is not a function of all the observations at previous times. So we can simplify that likelihood, the first term in the numerator of 7, to a simpler term, P of the probability of the observations given the current state. And as I said, we'll ignore the denominator. It could be written as an integral below. And so our general description of the forecast problem applying Bayes, the analysis step now looks, or assimilation step now looks like this. We want to get our posterior or analysis. It's the product of our likelihood, which is information about our observing system conditioned on the current state of our model, and the prior, which is the state of our model, a forecast given the observations from previous times. Okay, and again, I think almost all of you are familiar with having seen this at some point or another. So I'm going to jump back now to a particular method for solving this forecast problem, the Kalman filter, which has been around since the late 50s, early 60s. The actual seminal paper is in 1963. And the Kalman filter solves this problem by making a ton of assumptions. The first thing is it makes assumptions about the forecast model, that the model is deterministic part, F, is linear, and that the stochastic part, G, is a Gaussian noise term. It also assumes that the model state vector, X, can be represented by a Gaussian distribution. It assumes that the forward operator H that maps from our state vector X to our observations Y is a linear operator. And it repeats one of the assumptions that we've already started with, that the noise associated with predicting what is observed is unbiased Gaussian stuff. So there's a lot of simplifications here. Nevertheless, the Kalman filter is extremely powerful. It's been used in many, many applications. The big initial one was doing deep space navigation for the Apollo mission. And at that point, it was possible to solve cases where the state vector had a size of 6. So the X, Y, and Z coordinate positions and the velocities in those 3. But it took a large computer from that time to do those computations. The reason the Kalman filter works so nicely, in fact, the Kalman filter process was known to Gauss a century plus before it became practical to do it computationally. And the key point is simply high school mathematics. That is that the product of d-dimensional, so arbitrary dimensional normal distributions with means mu1 and mu2, so those are the vectors of the means in d dimensions, and covariance matrices, d by d matrices, sigma 1 and sigma 2. So on the left here, I have two normals, mu1, sigma 1, mu2, sigma 2, and the product of those is itself a normal with the weight term c and covariances and means that are easily computable. The covariance sigma of the product is simply the inverse of the inverse sums of the covariances. And the mean is the inverse covariance weighted mean of the prior means. And so mu1 is weighted by the inverse of its covariance, sigma 1. Mu2 is weighted by the inverse of its covariance, sigma 2. And so if mu1 has a larger covariance, it has more uncertainty, it will receive less weight because it's weighted by the inverse of that uncertainty. The C term is a little bit more complicated, but we're not going to have to worry about it in the specific algorithms we'll consider today. So given that algebraic result that the product of two normals is normal, and the assumptions that were made for the Kalman filter, that the state is X is a normal distribution or Gaussian, and that the observation forward operator H is Gaussian, then the Kalman filter simply becomes computing the product of two normal distributions in the numerator of equation 10 here. And the result is a normal distribution on the left. And the computation is trivial. Now, the challenge, well, first of all, let's just review this. As I said, I'm more of a visual thinker than a mathematical one. And one can also take a look at what the Kalman filter looks like pictorially here. So hypothetically, let's suppose we have a two-dimensional distribution from a forecast model, which is just the relative humidity at two different places. Maybe one of them is in Dulles Airport in DC, and the other one is in Baltimore. And so our prior distribution shown in green here is a result from our forecast model. The forecast for this morning says that, well, the probability is that the relative humidities are about 50 and 40%, and there's quite a bit of uncertainty shown with this. So I've simply plotted that as a function of two-dimensional space here in green. I then have some observations. In this case, they're nice and simple. They're just observations of the relative humidity at those two locations. And the instrument designers have told us that there is a specific type of uncertainty that's normal associated with those. And in this particular case, they're shown as being uncorrelated errors. And so I get a two-dimensional normal distribution shown in red associated with the likelihood too. That result I showed earlier, that the product of two normals is a normal, says that the posterior, the analysis on the left, is itself a normal. And if we went back and looked at those equations, this is consistent with them. The first thing is that, as I mentioned, the mean of the posterior is just a weighted sum of the likelihood and the prior. And so the spike of the blue normal distribution lies on the line between the mean of the green and the red. Because it's the inverse of the inverse covariances that's summed up, there is less uncertainty in the posterior, and that makes sense. We've combined two pieces of information, so we expect less uncertainty. So the blue is higher and narrower than either the green or red. And the blue is closer to whichever of the green or red has less uncertainty. In this case, it's a little hard to see this figure, but the green had a little bit less uncertainty, and so the blue is just a little bit closer to it. And so the Kalman filter is just this. In 2 dimensions, it's easy to visualize. In D dimensions, the computation will be the same, but it's a little bit harder to think about visualizing it. So as I mentioned, people were able to apply this on state-of-the-art computers in the early 60s for 6-dimensional problems. It would be easy enough to do a 6-dimensional problem on anyone who still wears a wristwatch. You don't need an Apple Watch to do this. But the challenge is that it is pretty expensive to compute this for larger problems. It requires computing the inverses of these D by D dimension covariance matrices. And the product of 2 of these covariance matrices is part of that. And so there's 2 issues here. The first thing is for big data assimilation problems. And some of the biggest problems that we do in my team are now moving into the billions of variables for the state vector and possibly into hundreds of millions of observations at any particular time. So it is very difficult to store the covariance matrices, which would be 1 billion times 1 billion elements. And it becomes too costly to explicitly invert those matrices, which is O of n squared, where n is the size of the problem. And so the Kalman filter is just kind of off the table for big applications. So there are solutions to this that were developed in the late 20th century and the earliest part of this century that use stochastic approximations or ensembles to compute some of the aspects of the Kalman filter. In today's talk, I'm not going to give you all the details of why these methods make things computationally affordable, but I am going to show you some ways they make other types of algorithmic enhancement possible. But schematically, this is how an ensemble Kalman filter works. I get an ensemble of forecasts. In this case, there are 20 little green dots here, which are 20 estimates from a model of the bivariate distribution of relative humidity at Dulles and in Baltimore. Now I'm going to proceed by simply fitting simple sample statistics a normal distribution to that. So I'm just going to compute the mean and covariance of that, and there's the plot of it. The observations are going to be the same as they were before. Those are simply information coming from people who build and know about instruments. And so I have a continuous representation of the prior in green and the likelihood in red. I can take the product as I outlined before and get a continuous distribution in blue. My remaining challenge is that now I need to make forecasts to the next time I'm going to assimilate, and I need to do that using an ensemble of state estimates. So somehow I have to use my prior ensemble in green and this continuous blue distribution, and I have to come up with a blue posterior ensemble. And there are a number of ways to do that, but one of the things is as long as the ensemble is big enough, there are ways to do that so the mean and covariance of the ensemble in blue are exactly the sample statistics of the continuous distribution shown in blue. And this is really how ensemble Kalman filters work. They convert an ensemble prior to a continuous distribution, a normal. They take a normal likelihood, they compute the product using standard functions of normals, and then they in some way find a sample of that posterior distribution. It turns out that there is another way to represent exactly that computation that makes it much simpler to extend and compute these capabilities. So the next few slides I'm going to show you are a schematic of a way to compute the Ensemble Kalman filter, and it's the way that we apply in Dart, our software. So in the lower left here, I have 3 blue asterisks at time t sub k, and each one of those asterisks represents a ensemble of the model state vector. So if the model is some big general circulation model that goes up to near space, that might be the gridded values of temperature, wind components, and a whole bunch of different tracer elements. And each one of those 3 has an ensemble forecast that differs in that. You can't really make this work in 3, but it's easier to show for the cartoon. So the first step is to make a forecast from our analysis at the previous time to time t sub k plus 1, where I have new observations that I want to assimilate. And so I get in this cartoon a 3-member ensemble prior estimate of the model state at time t sub k plus 1. Now, it turns out that without loss of generality, in fact, in identical solution, you can assimilate the observations one at a time as long as they do not have a correlated observation error. And there are solutions to that correlated problem, but let's not worry about that today. So let's assume that we have a large set of observations at time t sub k plus 1, but their errors are uncorrelated. So I'm just going to pick one of them sort of at random, the first one I want to assimilate. And I'll apply the forward operator from the model state X to get an estimate of what that instrument would have observed. And so that y-axis at the top left of the figure is now the value of my first observation. And as said, maybe that observation is relative humidity at Dulles Airport. And my forward operator involved just a interpolation from the model grid points of moisture to the location of the airport. Whatever the case, I now have 3 prior estimates shown as the green slashes of my observed quantity y. And I also have, from the instrument itself, the value that the instrument observed, shown as the red slash, and an estimate, in this case, a normal estimate of the error associated with that. And it turns out that the likelihood is the observation error centered around the observation. So I have, at this point, a normal for the likelihood of y and an ensemble for the prior. And now I'm just going to do a one-dimensional ensemble Kalman filter in this space, as I showed in the previous thing. So the first step is I'm going to fit a normal distribution. I'll show more detail of this in a moment. I'm going to take the product, and I'm going to compute a posterior ensemble for this observed value y. And so that is shown as the blue elements in the upper right figure. And I get associated increments that change from my prior estimate for each ensemble member to my posterior estimate shown in blue. The final step of the Ensemble Kalman filter in this case then is a linear regression using the bivariate prior statistics of the model quantity that I want to update and the observed quantity y. And it turns out that, again, for the Kalman filter, these regressions can be done entirely independently. So if I have a billion state variables in my model, I can update all of them, the impact of this observation y on all of them in parallel at the same time. And so you can get quite a bit of computational efficiency on large parallel machines. So now I've finished updating my model state from this first observation. I can take the second observation available at this time and do exactly the same thing, compute the forward operator, compute the increments for the scalar problem, regress those increments on all of the state variables. And I can continue to do that until I've assimilated all the observations available at this time. And once that's done, I have a new analysis. I can integrate that analysis ensemble to the next time t sub k plus 2 at which I have observations and do the whole thing over again. I'm going to pause briefly here and take a quick drink and give anyone who has a question about this procedure a chance to ask that question. Okay, I will push forward there. So the way I've described things to you is, as I said, properly implemented, exactly implementation of the Kalman filter. So let's zoom in for a minute on this scalar problem that happened for the observed variable y. How do I compute the increments for that? And so here is a cartoon just of that. Let's suppose I have a 5-member prior ensemble now, and let's say it's for the temperature here in Boulder this morning, where it's just about freezing. So I have this 5-member estimate, and I'm going to follow the procedure I outlined before in many dimensions. I'm going to compute the mean and standard deviation to get a prior continuous PDF that fits that ensemble. I'm going to assume that I have an observation here of 1 degree and that the instrument builders told me that it's plus or minus 1 on that. So I get a likelihood shown in red. I now take the particularly simple scalar product of 2 normals to get a posterior continuous distribution shown in blue. And now I have to find a posterior ensemble with 5 members that is consistent with that blue posterior distribution. And one way to do that is to first shift the 5 prior ensemble members so that their mean is exactly the mean of the posterior continuous PDF. And then I can linearly contract them around that mean so that they have the same sample standard deviation as that posterior PDF. And it turns out that doing this is exactly the same as getting the Kalman filter statistics again. And so each one of the observed quantities y, we will do this process for them. Now, I'll also show exactly how we do that second step, given the increments for one observation y, say the temperature here in Boulder, how we update the state variables. As I said, it's literally simple linear regression. This figure is a little bit unusual, but let's look at the large square center part. The horizontal axis is the observed variable. So that was the temperature, say, measured here where I'm sitting in the NCAR lab. The unobserved variable is, say, a temperature for a model grid point somewhere out in Kansas. And I have 5 ensemble members in my prior, and their joint distribution is shown in the big square plot. And so you can see they are roughly correlated. So most of the ones that are warmer for the observation are warmer for the state variable. And I've shown these little rectangular areas on the bottom and the side. Those are actually just the marginal distributions for the observed variable and the unobserved state variable. So I'm going to do what I described a moment ago to compute increments for my ensemble of the observed variable. And those increments are shown in blue in the lower plot. I'm then going to regress those increments onto the state variable. And I'm just going to do this by finding a standard least squares fit. I'm going to project my increments onto that slope of that least squares fit. And one of them, the one near the top, is highlighted with a slightly darker blue. And then I'm going to project those things over onto my left axis to get the blue increments over there. And so the increments for my unobserved state variable are now shown in the blues there. And you can see it did mostly what you would expect. The observation in this case suggested that it was warmer than my prior forecasts. They're roughly correlated positively. And so the application of this observation led to a warmer distribution for the unobserved state variable. Okay, so it turns out that this is all there is to a standard ensemble Kalman filter. And you can do this for an arbitrarily large number of observations and an arbitrarily large number of state variables. And these things have been around now for 20 years. So now I'm going to go into the new stuff. I'm going to introduce some more general methods for each of these 2 parts. So I'm going to start with this one-dimensional problem for observations. For those of you who haven't visited us, this is the NCAR lab where I am talking to you from this morning. It actually looks quite a bit like this morning. We had some fresh snow last night. Those of you who know me are also aware that I commute exclusively by bicycle, which involves going down a 1,000-foot vertical drop road by the Mesa lab here. And so I'm very interested in the road conditions when I come up or leave in the morning. So I'm just going to give a hypothetical idealized problem here. Suppose I want to know if there's ice on the hill to see how careful I need to be biking down. So on the top axis here, I have again an example of a forecast model prior. It's 10 forecasts of the temperature at NCAR this morning, and they're all positive. And I have an observation from a thermistor outside on a mast here. It says that the observation is about 0 and that there's an uncertainty of plus or minus 1. And so I do the same old thing. I fit a normal to my prior. I take the product to get a continuous posterior with Bayes. I do this update method to get an updated ensemble shown in blue. And there's 10 of these things. It turns out that 4 of them are less than 0. And so I might naively interpret this as being a 4 out of 10 or 40% chance that there's ice on the hill. And so I probably want to be careful. Now, the next thing I'm going to do is I'm going to show exactly these same plots. I'm just going to relabel the axis. So not every day is a pleasant, beautiful, snow-covered morning at NCAR. This is a picture of the NCAR fire a little bit more than 2 years ago now. And on this day, I might have been concerned about air quality going down the hill as opposed to ice. And so let's say now I relabel the horizontal axis. It used to be temperature, now it's ozone concentration. And I keep exactly the same forecast prior. I have 10 forecasts of ozone concentration. I have an observation that says the ozone concentration is relatively low. And because I'm working with an Ensemble Kalman filter, the likelihood for that observation has to be normal. And so it's exactly the same thing shown in red. This should already be concerning some of you who've thought about this problem. I take exactly the same process. I compute the continuous blue. I compute a sample of that blue, and I end up with 4 of those being negative. So 4 of them tells me the ozone concentration is going to be negative. And so that seems problematic. And if I'm going to put that back in a model, a lot of forecast models are going to crash when they see that negative concentration. So the first extension I'm going to talk about is the ability to use arbitrary continuous distribution fits that are consistent with things I know about a variable. So in this case, for the ozone, where I know that it's positive definite, I'm going to say, instead of fitting a normal distribution, I'm going to fit a gamma distribution shown here, which is itself positive definite. And I'm going to work with my instrument folks to get a distribution for the observation likelihood that is also a gamma. It turns out that the product of a gamma with a gamma is nicely a gamma, shown as the blue continuous. And our recent innovations have shown us how to get a posterior sample of that distribution. That's something that we didn't really know how to do up until recently. This lets us use more information from observation experts, because obviously the errors on something that's measuring ozone don't have tails that go negative. So there's probably some nice collaborative works there for observations that are important to space weather observations. I will quickly tell you too what this methodology for getting the posterior ensemble sample of the blue continuous thing is. And the method we use is called quantile conservation. These things are called quantile conserving ensemble filters. If I go back and look at my prior continuous distribution, the gamma shown in the top panel, and the ensemble members there, I can apply the CDF, the cumulative distribution function, for that distribution to each of those ensemble members. That's just computing the quantiles of those ensemble members in the distribution. And if I conserve those quantile members and get my posterior ensemble members so that they have the same quantiles in that blue posterior distribution, that's how this method works. So as an example, the largest ensemble member had a prior quantile of 0.87. And so in the posterior down at the bottom, it also has a quantile of 0.87. Let's skip this for a minute. And so Dart now can provide support for any continuous prior distribution that is fit to a thing. And so there's much more capability to do bounded quantities, to do quantities where you know things are non-normal. And later I'll show you a completely general non-parametric method for fitting priors to if you simply have no idea what the prior may be like. Again, jump in with questions if you have them, please.
Jeff, there is one question on a chart, but is this parallel procedure what's currently in Manhattan version of Dart?
Yes, so this is the Manhattan version of Dart does implement the regressions in parallel. And so that's where most of the parallel performance comes. The Manhattan version also computes forward operators in parallel and vectorized. And so that also adds speed to Dart. Please follow up in the chat or as a spoken question if you have more. Was that the only question, Tomoko?
So far.
Okay,
Thank you.
great, thanks. So it turns out that even if we allow general distributions for that scalar problem, we can immediately sort of lose a lot of the advantage when we do the regression. And so here is an example of that problem. Again, I'm showing here a bivariate distribution. In this case, the horizontal axis is for the observed temperature. Again, let's say here at NCAR. But the vertical axis is an unobserved grid point value of ozone concentration from our model. And so the vertical axis is positive definite. And the relationship between these two variables is a gamma versus a normal. It's approximately a cubic distribution here. And so the green ensemble members show a 100-member sample from this idealized problem. And the underlying gray shadings show an MCMC estimate of the actual distribution. And so if I apply my standard normal distribution for temperature, which is usually a pretty normal distribution, and then regress those increments from this temperature observation onto the ozone, I get a posterior distribution that looks like this. First of all, the analytic estimate is shown in gray, so that's what we really want. But what we really get are a whole bunch of negative ozone values, which clearly we don't want again. And we get a bunch of values that are outside of the distribution because it's not respecting anything about the curvature. So I'm going to move to the next slide, and it's going to show exactly the same green dots as in the left panel here, just without the gray shading. And so these are the same prior 100 ensemble members. And what I've done here is I've just highlighted 10 of those. And I've put on the increment vectors that are computed from those. So remember, those blue increment vectors are obtained by first computing the increment for the temperature in the horizontal axis, and then regressing those onto the least squares fit line, which is shown here as the black dashed line. And you can see immediately why we ended up getting some negative values. This regression knows nothing about the fact that 0 is a special value for the y-axis, and so it happily moves things along parallel to the regression line. So this is a problem. We've lost the advantages we got by doing our observed quantity. And so we're going to use a method that is now being widely applied in machine learning. It's been floating around in data assimilation for years under the name of Gaussian anamorphosis. The key point here is, however, we're going to apply it in this sequential process that I've shown, where you can do one observation at a time. And that allows us to do some things that have not been available before. So what we're actually going to do here is we're going to make a pair of univariate transformations to the individual scalar values here. So we're going to transform the x and y axis here independently, but with the same type of transform. So the first thing we're going to do is, in the same way that we did it for the scalar update, is we're going to pick an appropriate class of probability distribution for the two variables. And in this idealized case, I'm going to say that temperature is normally distributed. So that's like the regular Kalman filter. But that ozone concentration on the vertical axis is a gamma distribution. And then I will fit a normal distribution and a gamma distribution to the two axes. And that will give me a PDF and a CDF for each of those. And the first transformation I will make is called a probability integral transform. It is simply replacing the value of each ensemble member with the quantile that is associated with it. This is, again, exactly what we did in the first step of the observation space thing. Quantiles are, of course, bounded between 0 and 1. And it turns out that if we picked the appropriate distribution, the quantiles will actually be now distributed from a uniform 0-1 distribution. And so this plot down here shows the result of applying this probability integral transform with a normal to the horizontal axis and a gamma to the vertical axis. So we get something that looks like this. We're then going to do a second very standard transformation, which is sometimes referred to as the Probit transform. It transforms a uniform 0-1 distribution to an unbounded normal 0-1 distribution. It is simply applying the quantile function, okay, that is the inverse of the CDF of the standard normal distribution. Okay, that quantile function is shown here in the blue plot, and we apply that independently to the horizontal and vertical axes, and we end up with something that looks like this. So now if we pick the right distributions, hypothetically, these greens are drawn from a normal 0-1 distribution in the horizontal axis and the vertical axis. Now, there's no guarantees of what's happening for the covariance of these things, and so problems can still arise. But as you'll see, this can help fix a lot of the problems we had. And what we do is we do the regression in this space. We convert the increments of the observation from the standard space and the prior, and that allows us to compute the blue vectors for the state variable, the observed quantity in this space. We regress it in this space, so we compute the least squares line in this space, and we get increments shown for 10 of the ensemble members in the blue here. And then we simply invert these transforms that we did back to the regular space. And here's the result. This is exactly the same problem on the left, But now when we do this regression in the transform space, instead of getting all the problematic ones we had before, we get the cyan values that are shown here. And by definition, none of them are negative, and they represent the curvature better too. There are reasons to believe that is a fairly general result, but one can certainly construct examples where it's not. Again, I don't want to waste the time at this point on the mathematics, but the math is easy to do these transforms. And as I've said, these transforms are routine. It's just the ways that they're applied here that makes the difference. I'll skip other examples. I quickly want to talk about non-parametric distribution called the bounded normal rank histogram 2. That is, in many cases, you may not know what distribution is right. Is this thing really a gamma? Is it really a normal? You may just know something about the bounds. And so one can actually construct a continuous prior distribution, which we need to do this method, directly from the ensemble members in the following way. I don't know with this example 5-member distribution anything about it, except that it's a random draw from this thing that I want. That's what I'm going to assume. And so if I make a random draw with 5 members, the probability that the actual value lies between any of them is actually 1/6. And this is fairly intuitive when you stop and think about it. If I have a bunch of people in a room and I randomly pick 5 of them and I see what their ages are, if I pick a 6th person now, the probability that that 6th person's age is lower than any of them is 1/6. So there's a 1/6 probability that that person is the youngest. There's a 1/6 probability that person is the eldest. There's also a 1/6 probability that person is the second youngest. And that's consistent to this way of defining a probability distribution function. 1/6 of the probability goes into each of the intervals between these draws. And then we have to do something on the tail, and we do kind of a fancy partitioning of a piece of a normal on the tails so that we end up with 1/6 of the probability in each one of these intervals. We can now use this CDFs of this type. The CDF associated with that funky PDF is shown in the bottom panel here. And then we can get the quantiles from this, which nicely enough happen to be just 1/5, 2/5, 3/5, 4/5 basically. And we can apply these methods. If we know that the quantity is bounded, we can modify this thing. And again, you don't need to get the details of this in the short time here, but there's a way to get this distribution that respects the boundedness of this thing. And in fact, this is the same example again, where instead of saying, I know that these ensembles are normal and gamma, I simply say, I have no idea what they are, so I'm going to use this naive method. And again, I get cyans that are quite a bit better than what I had gotten in the linear regression case. Again, questions at this point, this has gone fairly fast, but the bottom line is there is a way to use standard transforms to do this regression. There is a way to get general probability distributions if you are just kind of ignorant about what the best choices would be that allow you to apply these methods.
Jeff, Tomoko, can you comment on a computational side? Are you?
Yeah, so that's an excellent question. And one of the key points of DART is that we are very interested in computational efficiency. So it turns out that in large applications that we do, for instance, reanalyses, problems that Nick Petitella does, I think Nick's on the call and we'll talk about it in a little while. So large application problems, the cost of these general methods is between 10 and 20% more than the standard methods. It requires sorting the ensemble, which is the biggest cost. It turns out that there can be very efficient sorting methods that work well in problems where you're doing forecast models. I won't go into that today, but the cost is really quite reasonable. And the parallelism is all retained because the regression is done exactly as it was done before. It is possible to construct cases that are more expensive, but not an order of magnitude more expensive. So again, we've had people now apply these new methods in their most general form in GCM reanalysis applications with fractional additional cost.
Thank you. There's one more. Do you want to take a question now?
Yeah.
Sorry, this is Umberto. Really quick question. When you say traditional methods, what are we talking about? We're talking about ensemble Kalman filter, or are we talking about the particle filter or the Gaussian mixture?
Yeah, it's
all
the
of
ensemble Kalman filter with normal distributions and standard linear regression is the baseline, Umberto.
Okay, thanks.
Okay, given this crowd and the fact that we're getting a little bit short on time, I'm not going to talk in detail about the Lorenz 96 model. If you don't know it, that's fine. But what I am going to introduce is an extension of the Lorenz 96 model. So plotted here in the left panel is a 40 variable version of Lorenz 96. So the 40 horizontal grid points associated with this idealized model are on the horizontal axis, and the time evolution of this apparently chaotic system are shown on the vertical axis. And so you can see that there's some complicated behavior here. What I'm going to do is treat the standard Lorenz 96 variable shown on the left there as a wind. And I'm going to let that wind advect a passive tracer on the same domain. And so the right panel has the same horizontal axis, 0 to 40, the same time in the vertical. And in this case, I'm emitting plumes of something. I'm going to think about it as a pollutant in the troposphere, but you could think of things that would be tracers that would be appearing in the upper atmosphere. So that plume is being emitted at grid point 1 here, and then the wind is blowing it across the domain. And normally this Lorenz 96 variable is positive, so normally you get plumes blowing from the source off to the right, but sometimes it reverses and blows back to the left. And I've highlighted in red 2 grid points here. A key point here is that this tracer rains out basically. And so when you get far from the source, the concentration of the tracer can be essentially 0. So you can see that in the white areas in the plot here. And what I'm going to do is apply these data assimilation methods, the new ones, nonlinear and non-Gaussian, to the traditional ensemble Kalman filters and look at the capabilities. I'm going to observe both the state, which is the wind, and the concentration infrequently at each one of the points with a simulated error. So this is an observing system simulation experiment. So this is a plot of the time behavior for the concentration of the pollutant at 2 of the grid points, grid point 14 in the top panel and 36 in the bottom. The one at the top is getting plumes that are blowing in from the left, and the one at the bottom getting plumes blowing in from the right. The truth in this OSSI is shown in blue, so you can see occasional plumes blowing in both places. And the ensemble, an 80-member ensemble estimate, is shown in green. The ensemble mean in red. And you can see this is a problem that has long been known for estimating these types of quantities in ensemble Kalman filters. You tend to be biased away from the boundary because you have these normal error distributions that don't know about the boundary. You can also, as we showed before, get negative. There's a few negatives that show up in the bottom panel here. And so this is problematic. I'm going to advance to the next slide here, which is going to keep the same blue curve, the same truth, and show the result of applying instead these new methods I've described. And so you can see that these methods, first of all, essentially eliminate this bias problem because they are aware of the boundary on the concentration at 0. They have significantly less error and significantly better spread to error ratios, which I will not have time to fully define today. And by definition, they can't go negative, but they can go to all 0, which is again something that traditional ensemble Kalman filters cannot do. And there's some specific times here, for instance, about day 50 on the lower panel, where all of the ensemble members do in fact go to an estimate of 0 concentration. I won't talk about it today. Using gammas, inverse gammas, or log normals for this can present some challenges compared to this distribution that I'm using. One can also try to estimate the sources with this. And so this is really a parameter estimation problem because the sources do not have a time evolution and are not part of this model. In the example I showed you, there was a source that was non-zero at grid point 1, and the source at all the other grid points was 0. And in this particular experiment now, in my assimilation, I started with very uncertain estimates of what the source was at all grid points, varying from 0 to 100. And then I let the assimilation try to estimate these parameters. And this is with traditional ensemble Kalman filters. The left panel is the error for the grid point where there is a source, and the right panel is the error for a grid point where there is no source as a function of time. And you can see that the errors for the ensemble members gradually converge. So the ensemble members collapse, the spread is lost, the error is reduced from the initial, And the error is relatively small. So again, we've known for a long time about this types of issues with estimating sources, model parameters that are bounded with traditional Ensemble Kalman filters. Again, by the way, time is the horizontal axis here. I'm now again going to scroll down and I'm going to show the same plots, but now with the new methods shown here. Basically, you get about 5 orders of magnitude less error for the grid point that has a source. And interestingly, in this particular example, you go to 0 error for the grid points that have no source. So eventually, all of the estimates in this 80-member ensemble case will go to 0. And this is a highly idealized problem, but nevertheless, there are a number of nice features of these new methods that come into play here. The ability to have duplicate members, the ability to represent the bound. I'm going to stop here with this really lightning overview of these methods and just quickly do an advertisement, which I have to do for Dart. So Dart is, as I said, a software facility for applying these types of methods. It can be done in low order models. It can be done in very large models. It runs on laptops. It runs on the largest supercomputers. It does not yet run efficiently on GPU systems, although that is on our long-term to-do list. The software is professionally software engineered, and we have a team that provides support, especially to university users. Dart works with several dozen large geoscience models. I've highlighted in red here. Sorry, I didn't relabel the thing, but I've highlighted models that may be of interest to some of you here. I guess GITM should have been highlighted too, but WACM-X, WACM, IGCM, ROSE are all models that have been used with Dart. Dart works with a very wide range of observing systems. Many of them have been used in the upper atmosphere. Just quickly, I want to shout out just example of the types of things that can be done. A number of you that are on this call have collaborated with us. Tomoko is definitely here. I think, as I said, Nick is here. This is an example of applications done by Nick Petitella with WACM-X with Dart, where he's doing cycling DA with basically the whole atmosphere. So he's assimilating weather observations in the troposphere. He's assimilating, not in this particular experiment, but he can assimilate cosmic electron density, golden icon winds, and other things in this case. And he's showing the impact of assimilating different observation sets on this. So this is an example of the types of things you can do in large models. So this is a big, expensive large model. This was run on NCAR supercomputing. It allows Nick to examine the impacts of these different observing systems. So this is just an example of the types of things that can be done. We've had a few questions. I want to leave time for a few more, so I'll actually start there. We have an unusually comprehensive and well-maintained assimilation documentation facility here at the website shown here. So we would encourage people who have more interest to take a visit there. You can also email us at places that are referenced there. And there are a number of papers. The most general audiences one is referenced at the bottom. So thanks very much for your attention and for the invitation. And I would love to have some questions.
Well, thank you, Jeff. Yeah. I think Adam is the one who is running, so I let him run it.
Yeah, I think Umberto has a question.
Jeffrey, thank you very much for this talk. This was pretty interesting and very, very informative. I had a couple of questions regarding your quantile method. Basically, this quantile method is, by what I've been reading, is meant to be able to handle nonlinear, non-Gaussian type of distributions. It was interesting to see that you can actually combine the distributions from different sources, either from model and observations and whatnot. And I wanted to I hope this is not an unfair question, but I wanted to ask you, have you guys compared this type of data simulation with something like the Gaussian mixture that's kind of old, and the particle filter? Particle filter has had a lot of advances to try to make it more affordable. Because in particle filter you're assuming you don't know anything about the distribution, right? And in here you're like, well, let's explore what's the distribution. If we can hit the right distribution with our prior knowledge, we can get really good results. So I don't know. That was my question.
It's a great question. It's completely fair. And so also thank you for answering it. And I think you've actually hit on the point that over the past quarter century, what's been going on in stochastic data assimilation has been a emotion from two ends. So Ensemble Kalman filters were developed in the late 90s. Particle filter methods were first applied in geoscience applications in the late 90s. And particle filters are completely general. Ensemble Kalman filters are quite simplified. Particle filters are incomprehensibly expensive. Ensemble Kalman filters are much more affordable. And so the theme over the past quarter century has been particle filter people trying to cut the computational cost by making simplifications, and Ensemble Kalman people trying to increase the complexity to get more generality.
Yes.
The first question you asked about Gaussian mixtures things is, it turns out that the whole reason I developed this stuff, you may or may not be aware, is I believe I introduced the concept of Gaussian mixtures in a paper, Anderson and Anderson, way back in 1999.
Yep.
And I was never able to find an efficient way to get the posterior distributions. And so what led to these quantile conserving things was the quantile conserving stuff will actually allow an efficient way to get ensemble posterior distributions from Gaussian mixture things.
Okay.
Now, it turns out that the Gaussian mixture things are actually have a surprising number of problems and are significantly more expensive than the distribution I showed here. But I would say further investigation is warranted for particular applications, and there are some people working on that. Now, as far as the particle filter methods, we also collaborate quite actively with Peter Jan van Leeuwen up at Colorado State and a number of his students, also with John Potterjoy at University of Maryland, people who have been coming the other way. And we have several particle filter variants implemented in Dart. At this point, I would say that if you can afford to apply some of those particle filter variants, I would expect them to be somewhat better than the best variants that I've described to you today.
Okay.
At present, even the least expensive of those remain significantly more expensive than these. And so the game's not over. You know, for the problem you have, what you can afford, the computing you have, the degree of nonlinearity, all these other things, none of these methods are a panacea. The advantage of the things I've described today is that they can be applied to large problems. And you saw that example of Nick with WACM-X, and you know, that's probably hundreds of millions of state variables there. You can apply them to large problems that are still out of computational reach for most of us on the particle variant methods. You know, active work is going on both sides. So you just have to keep your eyes open on the application that you want. And at the end of the day, my experience has always been, even in cases where it looks like it's obvious analytically how things are going to play out, unless you actually test these things, there's always a surprise when you really do it on relative timing and relative capability. So my answer is, you're right. These things should be checked. Haven't checked them comprehensively for a lot of applications.
Thank you. Thank you.
Do we have any other questions for Jeff?
And I'm happy to get email questions. I've been able to see who's still with us here. I know a number of you, and the rest of you look really friendly. So if you want to send an email with questions or anything else, my email's on the website, and I think it will probably be off the links too. But anyway, it'd be great to talk to any of you in the future about stuff.
Jeff, I know, you know, I just want to ask you a question about tutorial things that the Dart team offers. Did you include this quantile? You call it
that's a great question, Tomoko. So I am giving a tutorial in China in June, and I will be upgrading the tutorial to include these things before that. At present, the MATLAB, the nice interactive tutorial, does not yet include these, but it will by the end of June, or else I'm going to be in big trouble.
Okay, So stay tuned. So
Yeah, that's right.
maybe I'll seek the info if you
Yeah, I'm
if
switching.
I could distribute to the newsletter. Well,
Yeah, that becomes my priority project actually next Monday. So that's what I'm starting on it. But good question.
Okay.
All right, seeing no questions since we're at the top of the hour, I just wanted to thank Jeff again for a really wonderful presentation. I learned a lot myself and really benefited from this. So thanks so much, Jeff. Please be on the lookout for this on our YouTube channel, and then we will hopefully see you all in a month for May for our next seminar series. So thanks again, and we will see you all soon.
Thank you.
Thanks, everyone.
Thank you.
See you.
See you.